Hi, this is Pre-Calculus, section 2.6, rational equations, and we want to look at asymptotes, vertical, horizontal, and slant, as well as holes, intercepts, and domain. And so we're going to give you some rational expressions, and we want you to figure out what is, for instance, the end behavior, and what's the behavior in and around a vertical asymptote. So let's look at the first example. These are just limits, and so we're going to be dealing with this notation as x approaches infinity and f of x is equal to x plus 1 over x minus 3. What does f of x approach? And so this would be end behavior, and I just put positive infinity, but actually we want to look at what happens when we go to positive infinity and negative infinity. It isn't always the same, but for a lot of our examples now it will be. All right, if we look at this one, this is the x plus 1 divided by x minus 3. First of all, you'll see a vertical asymptote at x minus 3. Well, why is that? Well, that's because we divide by 0 when x is 3, and we can't divide by 0. So we're going to be undefined at this vertical asymptote. And when we go to this vertical asymptote, we either go to positive infinity or negative infinity. It depends what the case might be. But going back to the question on your sheet, it asks what is our behavior as we go way out there. Now, it's not obvious to see from this graph. You could change your window and make a lot of y's, but I'm going to go to my table. So for instance, if I plug in 100, I see that my y values from this function are going to be 1.04. How about if I plug in 1,000? Why would I plug in 1,000? Well, I didn't do very well there. Why would I plug in 1,000? Well, we're going to infinity, so we want to get some big numbers. So let's crank this up and see what we're doing. And I think, as you can see, oh, it says it's exactly 1. Oh my gosh, that's beautiful. Oh no, wait a second, it's not exactly 1. Oh, okay. It's going to approach 1, but it's not going to be exactly there. I'm going to get an error here, so I can jump on top of it and get this value. And so it does look like, though, that I'm approaching 1. And so in this situation, I am approaching 1. So I go back to my sheet here, and I'm going to say that f of x would approach 1. And we can look also when we go for negative infinity. How about if I go negative, let me plug in a negative big number. So as I go to negative, it also says 1, but once again we got a little bit of error. So this one's approaching from the underside. So when I'm going to the left, I'm approaching from the underside, and when I'm going from the right, I'm approaching the top side. And that's what this graph bears out: underside, top side. And then so going back to these problems, I want you to go try to figure out what would be the limit as x goes to infinity of this f of x. Try those now, and I'll have the answers for you in a minute. Now, you should have got 7/4 for this second one and 2/3 for this other one. Now, look at these values and see how they relate to your equations. Well, it turns out that for the degree of the polynomial, if the degree is the same, top and bottom, all you do is take the coefficients. Why would that be? Well, if I take a huge number and square it, it's going to drown out these values, and these values become insignificant. So you could actually cover up these values with your hand. You can't really cross them off because that's not a legal operation, but you can cover up these with your hand and say for big X, this is going to behave like 7x squared over 4x squared. X squareds cancel, so it's like 7/4. Here, this is a third degree polynomial. This is a third degree polynomial. Take the coefficients, the leading coefficients, and you get 2/3. What I like to do is mix these up sometimes, and you have to dig in there and see that the polynomial, the leading coefficients might not be at the front, and sometimes you just got to look at and see what the degree of the polynomial is. But you can take those coefficients. Now, what if the degree is not the same? Well, let me ask you this: what's 1 over a big number? And I hope that you say like 1 over a billion is a very small number. And what's 1 over a small number? Well, that would be a big number. So what happens when I look at a situation like this? Well, if I look at this, the bottom is growing faster than the top as x goes to infinity. And this is all for x going to infinity. So the bottom is going to go off to infinity at a much faster rate than this top is. So that would fall under this category. What's 1 over a big number? Now, it's not exactly 1, but the bottom's growing faster. So this would actually become a very small number. Well, a small number that we're looking at would be 0. And you can verify that with your calculator and your graphs. So if the denominator has a degree that's higher than the top, then as x goes to infinity, we're going to be going to 0. Now, we're going to get into what we call rational expressions. And rational, in this case, it's an equation. We call it n of x over d of x. N is the numerator, d is the denominator. The domain. This includes all values of x except for the x values where d of x is equal to 0. Obviously, you can't have that. Okay? And so we want to find those x values, and that is where we get our vertical asymptotes. And so the line x equal to a is a vertical asymptote of f if f approaches infinity or f approaches negative infinity as x approaches a. And then we have a vertical asymptote. And so if we're dividing by 0, that is where that's going to happen. Then we also have what we call a horizontal asymptote. And this is the line y equal to b. And let me note that you have to write these as equations. I don't want to see a vertical asymptote, oh, it's 3. No. X equal to 3 would be an example. This for a horizontal asymptote, you'd write y is equal to 9, for instance. Okay? So the line y equal to b is a horizontal asymptote of the graph of f if f of x approaches b as x approaches infinity or negative infinity. Another term for this is the end behavior is similar to y equal to b. And we can look at that on our calculator. If I graph, back to example 1, if I graph y equal to 1, and then I change my window a little bit and increase my x's, and I graph this, y equal to 1 and my curve look like the same thing. They're not exactly, but that's what our end behavior somewhat dictates. All right, now going back to the sheet. Slant asymptotes. That's when the degree of the numerator is 1 higher than the denominator. And this end behavior, well, what if you divide a cubic divided by a quadratic? You're going to end up with a linear. Okay? And so you could say y equals mx plus b. Then a hole. A hole occurs in a graph when factors cancel. Polynomial factors cancel. So for instance, if I have x plus 3 over x plus 3, one in the numerator, one in the denominator, they would cancel and we get a different behavior, but then we're still undefined at x equal to negative 3. But it's not a vertical asymptote. It's going to be a hole in the graph. Some of you have seen that before. Let me go back for a second and talk about these horizontal asymptotes. And with these horizontal asymptotes, I can go back up here and look at these equations. And when I see this end behavior, I know that now my horizontal asymptote for this one would be y equal to 1. So my horizontal asymptote is y equal to 1. This one, the horizontal asymptote would be y equal to 7/4. That's my end behavior. And then this one would be y is equal to 2/3. Those are all my horizontal asymptotes. I also can do my vertical asymptotes. We'll get into this more, but right for this one, it's when the denominator is equal to 0. So that would be x equal to 3. Notice the equations I write. Horizontal asymptote, y equal to. Vertical asymptote, x equal to 3. I'd have to factor those and figure those out. I'm not going to do that right now. We'll get into some other examples. All right, now, number one, we have this this rational expression here, and we want to graph this, so we state the domain. Well, it's going to be all reals except for x can't be 3. So that's our domain. Then B, identify all intercepts. X intercepts when y is equal to 0. And when y is equal to 0, we get, and if we set this up, we get y is equal to 0. And so when we set y equal to 0, we're going to get 0 is equal to negative 1 over x minus 3. When I cross multiply, the x drops out, and so I don't have any values. So there is no x-intercept. And then y-intercept is when x is equal to 0. And what happens there is that I'm going to get positive 1/3. And that would be my y-intercept. My vertical asymptote is going to be when x is equal to 3, because I can't do division by 0. It's the value of x that makes this 0. And then my horizontal asymptote deals with my end behavior. My end behavior for this one is that as x goes to infinity, well, the bottom is going to keep on growing. Without bound, the numerator stays the same, so it's growing faster than the numerator, so this will become a very small number. That small number would be y equal to 0. So now we can sketch this. At y equal to 0, we're going to have a horizontal asymptote. X equal to 3, we're going to have a vertical asymptote. I have a intercept at 0, 1/3. And then I should figure out how I'm approaching this vertical asymptote. And all you have to do, you know that it's going to go to positive infinity or negative infinity. So let's take a point that's pretty close and see if it's positive or negative. If it's positive, it's going up this way. If it's negative, it's going down this way. So let's take something close to that value. How about 2? If I plug in 2, this would be a negative, and this would be a negative. Negative divided by a negative is a positive. So that tells me that as I approach this asymptote from the left side, I'm going to go to positive infinity. Take a point on the right side. How about 4? This would be a negative. 4 minus 3 is positive, so that overall would be negative. So I'm going to be approaching this side. So you can kind of maybe see the shape that's building here. We're going to get that, and we're going to get that piece, and that's our curve. The key point here, though, is that as we approach this vertical asymptote, we're either going to positive infinity or negative infinity. It could be both, positive on both sides, whatever. But check a point near the vertical asymptote on the left. If it's positive, you're going to positive infinity. Check near on the right side. If it's negative infinity, it's going to negative infinity. You just have to make sure that you're close enough in. Okay, let's look at some more examples. This one we can factor. So if we can factor this one, let me just pause this and you pause it too and go. Okay, I got up to the point where I have vertical asymptotes. Now you might say that the vertical asymptotes are, well, when we divide by 0, so x equal to 3 and x equal to negative 3. If I go ahead and graph this, this is kind of cheating if I'm trying to graph this by hand, but look at this. I don't have any vertical asymptote at negative 3. And the question is why do I not? I have one at x equal to positive 3, but not at x equal to negative 3. Well, this comes out with the fact that I have these factors that can cancel. This one and this one. So in other words, this graph will behave exactly like x minus 5 over x minus 3 everywhere except for at x equal to negative 3. And what happens when we can cancel? Here we'll get a hole. So this is not a vertical asymptote. I'll cross that off. Nor is it an x-intercept because it canceled off there too. So we just have a vertical asymptote at x equal to 3, and what ends up happening is that we get a hole at x equal to negative 3. My horizontal asymptote, I guess I didn't write that there, horizontal asymptote then would be, take the coefficients. The leading coefficients here would be 1 over 1, so that would be y equal to 1. So now I have enough information to get a lot of this going. Here's my horizontal asymptote. My vertical asymptote is at x equal to 3. And then when I graph this, I figure out what's my behavior in and around this vertical asymptote here. Well, if I take the value of 4, plug it into what remains here, this would be a negative. I don't even need to find the value. And this would be a positive. What's a negative divided by a positive? Well, it's a negative. So there's my behavior in and around that vertical asymptote. Pick a value on this other side. How about 2? This would be a negative. This would be a negative. Negative divided by a negative is a positive. So that's my behavior there. And so I'm going to get this, and it's going to approach here. I got to be careful because I'm going to get this hole. So we demark it with a hole. And then it's going to go towards my horizontal asymptote. And then this one's going to go here. There's my graph. If you want to plot additional points, you may. One point that I did neglect is this 5/3, the y-intercept, but I look like I hit that though. I did okay by accident, but I should mark that one. That would be my y-intercept. Okay, let's look at this one. This one will deal with the slant asymptote. Try to do as much of this as you can, and then come back and I'll explain. Sorry, going back here for a second, I neglected this x-intercept too. Okay, the next one we got to deal with the slant asymptote. The degree of the numerator is 1 higher than the degree of the denominator. So when that happens, this will behave like a line for big values of x. Well, I can do the rabbit method on this. So y is equal to x plus 5 over x. So I just take this and divide here. And so for big X, as x goes to infinity, what happens to 5 over x? Just this piece. Well, 5 over x is going to go to 0 because the bottom keeps on growing bigger and bigger and bigger. And then it will behave just like this thing, whatever this is. And so my slant asymptote is going to be y equal to x. So my end behavior is going to look like this line right across here. And that would be my slant. I can kind of dot that in. Now, in and around this area, it's going to be much different, though, because I do have a vertical asymptote at 0. And so I'm going to be approaching, well, I can check on each side what I'm approaching. So if I'm at 1, if I plug in 1 into here, I'm going to get a positive. So I'm going to positive infinity. If I plug in a -1, -1, this would be positive, and this would be negative. So I'm going to negative infinity. So maybe we can get our shape from this. You might want to plot some other values to kind of figure this out, but really I'm going to, and I do want you to plot more, but I'm just going to give you a general shape. I'm going to be going like this. And what do you think this one's going to be doing? It's got to approach this line somehow. So it's going to be going like this. I don't know if it crosses there or not. I don't think it does. You can cross multiply and figure it out, but that's what the shape of this graph is going to look like. Let's do one with a more complex slant asymptote. If I look at this one, degree of the numerator is bigger than the degree of the denominator. For this one, to find the slant, really what you're supposed to do is do long division. So I'm going to take x cubed and see if I can get 2x squared minus 8 into that. Go ahead and do that, and I'm going to fill it. So if I do long division on this one, I end up with 1/2 x plus a remainder of 4x. So I take that remainder and I put it over the divisor. So what happens is that this thing right here, well, you tell me. What happens as x goes to infinity for this term? What's growing faster? Well, the denominator is going to growing faster, so this whole thing is going to go to 0. This will behave like 1/2 x. So my slant asymptote is y equal to 1/2 x. And so that's going to be, sorry, it's not exact in here, but it's a slope of 1/2, like that. Vertical asymptote. Do I have a vertical asymptote? 2x squared minus 8 equal to 0. X squared is equal to 4, so x is equal to plus or minus 2. That works for us, and we're going to have a 0 here. So plus or minus 2. And a 0 here. How do I approach? Oh, I missed the 2. Let me pause and get this going. Okay, let's figure out our behavior near these vertical asymptotes. So if I come from the left side, let's plug -3 in here. Do we get a positive or negative? Numerator would be negative, and denominator would be, well, 3 squared is 9 times 2. That would be a positive. So a negative divided by a positive is a negative. So I'm going to be approaching negative infinity here. Plug in -1. If I plug in -1, this would be negative. And then this one would be negative as well. So overall, I would have a positive value here. And then I plug in 1. 1 is positive there, and we'd be negative there. So overall, that's negative. And plug in 3, that would be positive. And this one, if I plug in 3, would be positive as well. So it's positive divided by positive, which would be a positive. So this positive here, I'm going up here. This one's a negative. I'm going here. I think I'm getting this shape down. This one's a positive. So I think this piece is going to go like this because I'm going to approach as this goes out. And then for this one here, I'm going to go like that, I believe, because I got to approach on both sides there. And then here, this keeps on coming undone. What do you think? Oh, I think so too. So we go that way. All right, that would be a start for us on graphing these rational expressions. We'll cover some more of this in class, and I hope you enjoyed this. Thanks.